So let's do another application of Gauss's law. Again, notice this Gauss's law stuff, we got a little bit of math in it, but I think it's actually a little bit easier than some of the stuff that we did in chapter 22. So let's consider a metal plate and another metal plate. So let's say both metal plates are large, so there's some separation D, but we're going to assume that the length of the metal plates, so from one end to the other, that length, we're going to assume is much greater than the separation. Okay, and so I'm going to put a charge Q1 onto the top one, Q2. Now I'm going to say the Q2 is 0, so I'm going to leave the bottom uncharged. And so the top one, Q1, is going to be 3 microcoulombs. And I want to know how the charge arranges itself in there. Okay. So we got 3 microcoulombs up here. Okay. Now, one thing we do know is that the electric field inside the conductor has to be 0. And so that means if you got charge on one side, you have to have charge on the other side so that the electric field cancels in between. So that means we have to have the same sigma on the top and the bottom. Okay. And so, so in that case, then that means the charge is going to be symmetric. Okay. And so that means that Q top and Q bottom are going to be symmetric. So Q top equals Q bottom. Okay, we know from what Gauss's law tells us about the electric fields in conductors. And so that means that the only way that works is if it's 1.5 microcoulombs. And so that means that we end up with 1.5 microcoulombs there and 1.5 microcoulombs there. Both of them positive. Now here's the problem. Okay, that means electric field going out. So this electric field going this way would go through there, except we can't go through there because that has to be 0 inside that other conducting sheet. So that means that this charge has to be the opposite of what that is. Because we know that the electric field is going to be sigma over epsilon naught, okay, for a conductor. And so that means this electric field in here is going to be constant. So that means that it's got to be the same sigma. Well, not exactly the same sigma because it's going away from the top and towards the bottom. So that means the bottom has to be minus 1.5 microcoulombs. But the total charge on the bottom plate is 0. So that means the other side has to be plus 1.5 microcoulombs. Okay, so you put 3 microcoulombs on the upper plate. It splits top and bottom. Okay, and so both top and bottom surfaces have 1.5 microcoulombs on them. So the sigma is going to be divided by the area of those plates. And I didn't say what that was, but if I gave you the area, you would find just divide by area. Okay, and then because of how conductors work and conducting sheets, that tells you what's got to be going on with the other one. Okay, so that's an application of this. So what would happen if we had 3 microcoulombs there and 3 microcoulombs there? Imagine now that we have a Gaussian surface here, and we've got a total here of 6 microcoulombs per area on top and bottom because of how this is all spread out. And so because it's symmetric, we're going to have the same going away from it in either direction. And so the only way this would work would be if we ended up with 3 microcoulombs there, 3 microcoulombs there, and 0 in between. Okay. Because these repel each other. Okay. So the net is going to be 6 microcoulombs that we see on this thing. And so if you get away from it, it's going to be symmetric. And so you got to have the same top and bottom. Okay. So let's make it a little more complicated now. Okay. So now let's say same situation, and I put, Q1 here is going to be plus 3 microcoulombs, and Q2 is going to be minus 1 microcoulomb. Okay, now we look at it and we say the net here. Now remember, when we had 3 and 0, we had 3 and the top and bottom looked the same. They each had 1.5. Okay, and so now the net is going to be 2 microcoulombs. So that means the top is going to be 1 microcoulomb. The bottom is going to be 1 microcoulomb. Well, there's a total of 3 microcoulombs up here. So that means we got to have plus 2 microcoulombs on the inner surface. Well, these two have to cancel each other. And so if this is plus 2 right there, this has to be minus 2 down here, minus 2 microcoulomb. That also makes sense because if you look at these two, the two added together give you minus 1 microcoulombs. And so again, this is again looking at it because we know the electric field in here has to be 0. And so any electric field here, any sigma here has to have a minus sigma right there on that other surface. And so minus sigma is Q over A. And so if you knew the area of these two plates, then that would, assume they have the same area, then this charge has to be, and this charge right here have to be negatives of each other. So let's do another example. Okay. So now let's say that what we do is we put 3 microcoulombs on the top one and 2 microcoulombs on the bottom. Okay, so you look at it, and again, it's got to be symmetric. Imagine drawing a Gaussian surface right here. The electric field's going away like that. The total is 5, so that means that spread top and bottom. So the top and bottom have to have 2.5 microcoulombs, because that's going to be half of this total right here. Okay, so the top one had 3 microcoulombs total, 2.5 microcoulombs is at the top, so the bottom has to be half of a microcoulomb. Okay, down here, that has to be equal and opposite of that, and the bottom has to add to 2 microcoulombs. So if you have 2.5 microcoulombs on the bottom surface, the upper surface has to be negative 0.5 microcoulombs. Okay, all right. So now, let's do one more example. Again, 2 metal plates. And now what I do is I put 3 microcoulombs on the top one and minus 3 microcoulombs on the bottom one. So you look at that and you say, imagine your Gaussian surface here. What's the total amount of charge enclosed? 0. So that means there's no sigma on the top and the bottom. So those are 0, and so that means this has to be 3 microcoulombs, and this has to be minus 3 microcoulombs in order for the total top and bottom here to add up to that, and the total top and bottom there to add up to this. And so hopefully this gives you an idea as to how to do this sort of thing. And again, this is just applications of Gauss's law to these large metal plates. And it might not look like a whole lot, but this is a very powerful tool right here for how you can see how the charges distribute themselves. And again, there's not a whole lot of math in here. What do? We added and subtracted. Okay, so this was not enormously difficult math, not compared to the integrals we've been doing earlier, but the concept is robust, and you have to stop and think about it a little bit more. And so that's the difficult part here is the thinking about it, not the actual mathematics. The mathematics is a whole lot easier than some of the stuff that we've done before, but the concepts are more involved.